In this lesson, I'm going to be covering some of the basic operations in R. We will become familiar with using R as a basic calculator, using all the operators and some popular mathematical expressions and functions. First, we need to create some variables. When you're assigning something to be a negative number, it can look like this, and R will recognize that this is the assign annotation, followed by a negative sign. Let's quickly go through some of the different operators. Addition is very simple, as long as your variables are numerics. Subtraction, very similar. We can multiply using the star, and we can divide using backslash. Now, if you want to raise something to a power, there are two ways to do that. I can either use the up arrow to square something if I want to use 2, or I can cube it using 3 instead. And instead of using that caret notation, you can also do a double star. So you can use those interchangeably. They mean the same thing. Let's talk about rounding real quick. Here's a variable that's stored in the R environment, pi, 3.14. We can round that very simply using the round function. And the round function takes 2 arguments. So it needs the number that you want to round, and it needs to know to what decimal place. So if you put 0, it's going to round it to the nearest whole integer, which is 3. Or if you want the familiar 3.14, you can enter 2 and it will return 2 decimal places. Some related functions are the floor and ceiling functions. If I do floor on pi, it's going to round it down to the nearest integer, which is 3. If I use the ceiling function, it's going to return 4 because it rounds up to the nearest whole integer. Now we also have access to all the trig functions. So we can do the cosine of pi, -1. Cosine of pi times 2, 1, or times 0.5. So you can see that we're now doing mathematic operations inside a function. And that's definitely allowable because it will first calculate what this value is, pi times 0.5, and then it will calculate what the cosine of that value is. That's very acceptable, and you'll probably end up doing that quite a bit. So there's sine, also tangent. If you want the inverse trig functions, all you have to do is add an a in front of the cosine, sine, or tangent functions. So it'd be a cos, a sine, a tan. We set the variable z to equal -3, and we can get the absolute value of that just by using abs. If we try to take the square root of z, it won't work because z is a negative number, but we can easily do the square root of the absolute value of z. So again, this is a function within a function, and it will calculate this first, the inside part, before it calculates the outside part. It's also known as a nested function. So if you want to raise a number to decimal power, you have to use some parentheses. This is the same thing as doing the square root of x. So I'm going to raise x to the half power. I need to put the 1 divided by 2 in parentheses first. Otherwise, it's just going to calculate x to the first power and then divide it by 2, which returns 5. So it's important to know when to use parentheses in situations like that. The log function and log10 function, which returns the logarithm of x with a 10 as a base. The log function has a base of 2.718, which is known as e. So if you want to know what the value e is, we can use the exp function. So if I enter 1 as the argument, it's going to return e. So if you want some more information about that, you can just use the question mark. It's going to give us logarithms and exponential functions. You can see that there are a few more that I didn't cover. Lastly, the factorial function. If you enter the factorial with a value of 4 as an argument, it's going to return 24. And this is the same thing as 1 times 2 times 3 times 4. In this lesson, I gave you an introduction to a handful of mathematical functions. Some of them we'll be using, but a lot of them we probably won't revisit. It's just good to know that they're there. At this point, I hope that you're beginning to understand that everything in R is an object. This includes variables, functions, and packages, whether written by you or a different user. These objects interact with each other to uncover useful information about the inputs put into the program. Basically, objects work on inputs to become objects. So far, we have talked about individual objects like simple variables. If I assign x to be 15, we now have an object, which is a single value, which is 15. We call it by using the tag x. What if we want more than one variable or one object to exist inside the x object? Let's introduce a new type of object, which is known as a vector. Define a vector using this C function. And we can enter in as many different values as we want, separated by commas. So now vec is a numerical vector. So whenever I enter it into the console, it's going to return the series of numbers 1 through 5. This is the simplest data structure we can have. It describes a group of things, and in this case, numerics. You can think of the C function as sort of like combining objects. In this case, it just simply grouped together the integers 1 through 5. We've entered 5 different arguments into that function, and there is a limit to how many arguments you can add. It's an extremely high number, like 2 to the 31st power. We can use the class function to get a little more information about the vector that we just created. The class function will tell you what is in that object, and in this case, it's all numerics. Now, we could create this same vector with less typing. So instead of using the C function and listing out each integer 1 through 5, we can just enter 1:5. What 1:5 does is it gives you the range of integers from 1 to 5. So if I do 3 through 7, it's going to return 3, 4, 5, 6, 7. This is very helpful notation, and we'll use this quite a bit. It also works for decimals. So if I do 1.5 through 5.5, it's going to return from 1.5 to 5.5, iterating by one integer at each point. The difference between each object in this vector is going to be 1. Our original vector has 5 objects. We can easily subset this vector by using square bracket notation. And if I enter 1, it's going to return the first value in that vector. I'm going to create a new one real quick just to make it more apparent what's going on. So I'm going to create a vector that's the integers 10 through 15. And we can see it here now. And let's look at that square notation again. If I enter 1 into square bracket notation directly after the object name, it's going to return the first object of that vector. If I enter 3, it'll return the third object, which is 12. Now we can use that same colon notation that I showed you before. If I enter 1:3 into the square bracket notation, it's going to return the first 3 objects of that vector. Similarly, if we enter a -1, it will return everything except the first object. If I do -3, it will return everything except that third object. So you can see that it skips 12. And if you want to skip a whole portion, you can do the 1:3 in parentheses and have a negative sign sitting right outside of it. That's going to return the last 3. Creating a vector by entering either a range or individual numbers is rather straightforward. We can even enter vectors into vectors or user-defined variables into vectors. So let me create a few vectors real quick. So I created 2 vectors and z, which is just a single number, 100. Now I can create a vector using the C function again and throwing these all into it. So I'm going to be combining 2 vectors and a single value. And now our vector is bigger. Contains 1, 2, 3, some decimals, and the value 100. How about instead of z, I want the range of numbers from -3 to -1. Length is a very useful function when dealing with these vectors. It tells us the number of elements that are inside of it. So if I do length of my vec, it's going to return 9. We can also create vectors out of strings. So if I do car vec, this is going to be a character vector. And I'm going to enter in the strings hello, hi, and sup. We can also do Boolean vectors. So if I do boo vec, I can do true, false, true, true. Now, if we try to create a vector out of numbers, strings, and Booleans, they're all coerced into strings. Here's the combine function. I'm going to try to enter a number, a string, and a Boolean object, a true. Now, when you do that, the only way to have all these objects be the same class is to do what's called coercion. it forces those objects to all be strings because they can all exist as strings. But for example, this object high cannot exist as a number or a Boolean object. Now, an important feature about these vectors is that we can do mathematical operations on them. So let's create our original vector again as the integers 1 through 5. I can do multiplication to this vector. And what it does is it's going to multiply each object by the number 2, as long as they're all numerics. Otherwise, it would fail. I can add vectors together. So if I add it to itself, you'll get the same thing. If I do vec plus 10, it's going to add 10 to each object. I can square them all. Let me create another vector, vec2, which is the numbers 1 through 5. And I'm going to multiply this by 2. So what this is going to do is it's going to give me a vector that's 2, 4, 6, 8, and 10. Now I can do some complex operations to both these vectors. So if I do 3 times vec, my original one, that's 1 through 5, and I add it to vec2 squared, then add another 1, and I divide the whole thing by 10, it will return these values. Basically, for each object, for each variable, so let's say the first object in each vector, it's going to take 1 times 3 plus 2 squared plus 1 divided by 10. Now, what if my vec2 had a longer length? So length of my vec2 is now 6. There's 6 objects in it, while my original vector has 5 objects. Now, if I try to do this operation, it's not going to work. You'll get a warning because one of the objects was longer than the other one. It ends up cutting off the last value that we added to the second vector. In this lesson, I gave you an introduction to vectors, how to create a vector, and how to do different mathematical operations on them. And we're going to be using this information a lot throughout the course. In this lesson, we're going to be talking about some special vector types known as sequences and repetitions. The first function I want to talk about is the sequence function. And this function takes 3 arguments. Let's learn a little bit more about the sequence function. So it generates a sequence, and there are a lot of ways to use this, but I'm going to show you the simplest way we can use it. If we use the tab completion on the sequence function, it will show you the different arguments. The 3 main ones that you need are from, to, and by. What this means is if I enter the numbers 1, 10, and 0.5, is that it's going to give you the range of numbers from 1 to 10, incrementing each step by 0.5. So if you enter that, it's going to return 1, 1.5, 2, 2.5, and so on until it hits the number 10. Now, if I were to enter 1 instead of 0.5, it returns the same thing as if I do 1 colon 10. Here's another example. I'm going to do each iteration by 0.01, and you can see that it returns around 900 different values. If I did 0 instead, it would return 1,000. We can also add a variable as the by argument. So if I want to see the values of 1 through 10, and for by, we'll set it to equal pi. Then it's going to give you 1. It's going to add 3.14 to be 4.14, and so on until it reaches 10. If we pass in a single number, let's say the number 5, it's just going to return the vector of integers from 1 through 5. When I'm writing a function like this, I'm sort of doing it shorthand. Really, what we're saying is we want the argument from to equal 1, the argument to equal 10, and the argument by to equal 0.5, like our original example. When I don't assign this value to the argument and just enter 1, 10, and 0.5, it's assuming that it's in the right order. It assumes that the 1 is going to be from, the 10 is going to be to, and the 0.5 is by. If we mixed up these arguments, it would give us an error or might not work the way we expect it to. So the reason that first one didn't work is because it's trying to go from 1 to 0.5 by a positive 10. So that doesn't really work. You can go from a higher number to a lower number, but then your by argument has to be negative. So let me show you a better example of that. Let's say we want to go from 0 to negative 10 by 0.5. It won't work, but if I do negative 0.5, then it works just fine. So let's compare the integers 1 through 5 with a sequence of 5 and see if they equal the same thing. And what it returns is a vector that is the same length as the vectors you're inspecting, and it will return a true or a false for each one. sequent 5 is 1, 2, 3, 4, 5, which is the same as 1 through 5. So when I ask it this logical question, are they equal to each other? What it's doing is that it's comparing this first object in the sequence to the first object in the range and asking if they're true. So for each one of those cases, it's true, and that's why it returns 5 trues. If you want to know if the vectors are just equal to each other, instead of knowing if each object in the vectors are equal to each other, we can use the all function. So if I enter this logical argument into the all function, it's asking, are all of the values true? This all function is basically saying, are all these Booleans that were returned true? And they are, so you get true. And if you put an exclamation point in front of the all, it's going to return false, because it's asking the opposite of that. The other function I want to introduce to you is the repetition function. If I use the repetition function, I'm going to enter in 2 arguments, 1 and 5. What this is doing is it's going to repeat this value this number of times. Now, I can also repeat a vector as many times as I want. So let's say I want to repeat the vector of values 1, 2, and 3 5 times. You'll see that it goes 1, 2, 3, 1, 2, 3, 1, 2, 3. We can also repeat character strings or Boolean objects. Here, it returns a vector, which is that string that I want to repeat, and it repeats it 100 times. Or you can repeat Boolean objects. These are pretty helpful ways to create vectors of numbers. The sequence is very useful, and it's very similar to using the colon notation, and both of those we're going to be using a lot. Now let's talk about some basic statistical functions, and these are functions that we can apply to simple vectors. Ahead of time, I've constructed a few vectors, the x vector, y vector, and z vector, and they're all numerical vectors. And let me source this right now, and our environment will be populated with those vectors. Now if I type xvec, you can see what that is, the y vector and the z vector, which just does mathematical operations on the x vector. Okay, so the first couple functions I want to talk about are the sum and length functions. And these are very simple. The sum function will sum up all of the values inside a vector. So when I do it on the x vector, it comes up with 45. The y vector comes up with 15.5. And the z vector comes up with negative 510. The length function is also pretty self-explanatory. It just tells you how many different objects are inside that vector. So we can see that all the vectors have 10 numbers inside of them. So there are also some very easy functions to begin describing our data. The min and max function, for example. The min function will return the minimum value inside of a vector, while the max function will return the maximum value. If you enter minimum of multiple vectors, it will give you the smallest value among both vectors combined. Now, a similar function, which will give you the minimum and maximum at the same time, is the range function. Because the range function outputs 2 different numbers, we can actually use the square bracket subsetting to get either the min or the max. So if I do range of the y vector with the 1 in square brackets following that, it's going to return the minimum, and the 2 will return the maximum. So let's look at averages now. If you want to get the average of a vector, use the mean function. If we try to enter multiple arguments into this, it's going to fail because you can only enter in 1 argument into the mean function, and it needs to be a vector or it can be a data matrix. Now, if you're interested in median, that's pretty self-explanatory as well. Just use the median function. Now, another useful statistic is the mean absolute deviation. It takes the median of the absolute deviations of the data set from the median and describes that variation or the spread of the data set. So that function is just called MAD. Some other measures of variation include variance and standard deviation. So for variance, we use VAR, and for standard deviation, we use SD. And of course, standard deviation is just the square root of the variance. So we can double check to make sure these functions are working properly by using the square root function. We'll put the variance of the x vector inside of that, and we're going to do a logical test to see if it equals the standard deviation of the x vector. So again, this double equal sign is asking a question. It's asking if the object on the left is equal to the object on the right. And it returns a Boolean object, which is true. Now, the standard deviation can tell us in the range of the mean plus or minus the standard deviation, we can find 68% of the observations, assuming normality. For 2 standard deviations, it's 95%. So we can test this really quickly. So I'm going to create a lower bound, which is going to be the mean of my z vector minus 1 standard deviation of the same vector. And then I'm going to create the same thing in upper bounds, but I'm going to add a standard deviation instead of subtract it. Next, I'm going to look for all observations which are greater than the lower bounds and less than the upper bound. So here, you can notice that I'm separating these two conditions by an and sign. So this and sign will return true for any of the objects in the z vector which are greater than the lower bounds and less than the upper bounds. So you can see it returns a series of false and trues. Now, if we want to count the number of trues, all we have to do is use the sum function, because the sum function works on numerics, and anytime a Boolean is true, if it's forced to numerics, it will become a 1. If it's false, it will become a 0. So we can see that in this lesson, I'm going to introduce how to construct and do simple operations on matrices. So far, we have really only seen vectors, and a vector can be seen as a one-dimensional object that has a length. A matrix takes that a step further. It's a two-dimensional data object. Each element of a matrix sits at the intersection of a row and a column. In this untitled script, we have a line that creates a matrix. And to create a matrix, you use the matrix function. You have to enter in, as the first argument, the data you're interested in, and the number of rows and number of columns. So let's run this line. We now have in our environment the A matrix. And when I have it output into the console, we can see what it looks like. So there are 2 rows and 3 columns. Now sometimes we want to transpose a matrix, which is pretty simple. And what a transpose does is it flips the numbers around the diagonal. So after we transpose the matrix A, we're going to end up with 3 rows and 2 columns. The transpose function is just the simple lowercase t. Now something interesting is that when you use the transpose function on a vector, it actually turns it into a 1-row matrix. So let's create a simple vector. I'm just going to have it be the numbers 1 through 5. We can use the dim function, which will tell us the dimensions of an object. So when we do dimensions of the vector, it's going to say null because it doesn't see it as a matrix. But now if we use the transpose function on the vector, we can see it has some more structure now. Whereas before it looks like this, now we can see it has 1 row and 5 columns. So if we ask for the dimensions of the transpose of a vector, it will give us 1 and 5. Now, if we want to know what the element is in the first row and third column of a data matrix, we can use the square bracket subset. We just have to give it another argument. So for example, if we want the second argument of the vector I just created, we use the square bracket subsetting and enter in the single digit 2. For the matrix, if we want what's in the first row and third column, for instance, we do 1, 3. What you put to the left of the comma defines the rows that are selected, and what you put to the right defines the column. So if we look at the A matrix again, we can see that this subsetting worked. It returned 4, which is correct. Now, if you try to subset for something that doesn't exist, for example, what's in the first row and the fourth column, it's going to say subscript out of bounds. And this is an error that you may come across pretty frequently. If you're just interested in a slice of the matrix, let's say you want the whole second column, you leave the left side blank and you do 2, and it returns 1 and 1. Or if you want just the first row, you leave the right side blank and put a 1 to the left of the comma. Now, generally, when you make a matrix, you don't always need to specify number of columns and number of rows. Generally, if you specify 1, it will figure out what the other one should be. So let's create a sequence of numbers, and we're going to say n row equals 7. And we're not going to specify number of columns. And it was able to figure out, based on the length of the sequence that I entered and the number of rows, what the number of columns is going to be. If you enter no argument for the number of rows or number of columns, it will just assume that number of columns equals 1. What if you want just the second and fifth rows? So we want to be able to separate this row and this row from the rest. Well, we can use the C function. So we have to put it to the left of the comma, put lowercase c, and then we'll put the 2 row numbers that we're interested in, 2 and 5. Another useful matrix building function is diag. This function creates an identity matrix, which is a square matrix with ones in the diagonal. So if I use the diag function and enter 5, it's going to return a 5 by 5 matrix with 1 at each diagonal. If you do diag 1, it just returns the number 1 in a 1 by 1 matrix. These diagonal functions are very crucial for matrix operations and exist as part of the code in many statistical packages. Mathematical operation works on matrices just like they do on vectors. So if I take my A matrix, I can multiply it by 2, and it will multiply everything in the matrix by 2. I can do the square root of the matrix A, and I can also square it. We can also add matrices to other matrices. So let's create another matrix called B. So now we have 2 matrices, A and B. And what do you think is going to happen if I try to add them together? In this lesson, we're going to go further into detail about matrices and matrix operations. So ahead of time, I wrote a little script that's going to create a couple fake data sets for us. So I'm going to source this script and then we can talk about what the code does. So here we have the A matrix. I created the A matrix by entering in a sequence of numbers into the matrix function and the number of columns that I'm interested in. I named the columns by using the colnames function. And I need to make sure that I have as many arguments in the C combined function as there are columns. For row names, I did a similar thing, except I used the paste function. And what this function does is it concatenates strings together. So if you look down in the console now, we'll see that I'm concatenating the string 3 with a backslash with the numbers 12 through 16. And this argument sep tells the function how to separate the different strings. And it may be hard to tell, but there's nothing in here. It's blank. It's not even a space. So when I run that, it pastes 3 backslash with the number 12 through 16 as strings. So you can think of these as dates: March 12th, March 13th, March 14th, and so on. What I've created here with the A dataset and the B dataset are sort of fake temperature datasets. Think of it that way. So we have Fairbanks, Alaska, San Francisco, Chicago, LA, Seattle, and Honolulu. Now, the first functions I want to show you are cbind and rbind. So how can we easily join these datasets? With the cbind function, it will join the datasets by column. So if I do cbind A and B as my arguments, it's going to put them side by side, slap them together. So now we have all the cities together along with their different days. There's also rbind, which binds the rows. In this case, there must be the same number of columns for it to work properly. Just as with cbind, there must be the same number of rows for each data set for it to work properly. This worked well because we have 5 rows for each data set. Let's say we captured the temperature of the next day for all these cities. So I'm going to create a data set called new data. And it's also going to be a matrix. And I'm just going to give it some random numbers, which might be the real temperatures. I think they're probably pretty close to average. And I'm going to say number of rows to equal 1. And then for the row name of this new data set, even though there's only one row, you still have to use the proper function, which is row names. I'm going to set it to be 317, which is the next day. And for column names of new data, I'm going to have it be the combination of the call names of A and the call names of B. So right now what I'm doing is sort of a trick. Instead of renaming all these 6 cities, I can just take the column names from A and the column names from B and paste them together. So now our new data looks like this. And if we want to add this to our old data, we can rbind it to the old data set. And because I didn't create a new data set out of the 2 original matrices A and B, I'm going to nest the cbind function inside of the rbind function. So first it's going to join together A and B using cbind, and then we're going to rbind the new data set to that matrix. And this is what it looks like. Another way to do this would have just been to create old data, which is the cbind of A and B, and then rbind old and new. Later on, we will discuss how to merge data sets when information is missing. For example, if we didn't have data on March 12th for the LA, Seattle, and Honolulu group, how could we cbind them with different numbers of rows? This will come later. For now, consider cbind and rbind to be very easy ways to join groups of information under the nice conditions of matching number of rows or columns. I'm going to create a new variable called full data as the rbind of the old and new. And then something interesting happens if you use the C function on a matrix. It actually deconstructs the matrix into a long vector. And we can get the number of elements of the data set by using the length function on that, or we could do something like this: the number of rows times the number of columns. Or similarly, we could even do dimension of full data, the first one, which is the number of rows, times the dimension of full data, you can see that there are a lot of different ways to do things. And generally what we want to do is find the simplest way to do it, the one that's easiest to understand, and the one that's the fastest. And we'll talk more about this later on as well. In this lesson, we talked a little bit more about matrices, and I introduced a couple new functions, namely the column names and row names, along with rbind and cbind. Very soon, we'll talk about running statistical functions on these data matrices. Now let's talk about applying basic statistical functions to data matrices. Ahead of time, I wrote a few lines of code just to get us started. And this includes some fake temperature data from different cities. So I'm going to source this information. And if I look at the last object created, temp data, it will show us the temperature for 6 different cities over 5 different days. Now we can use simple functions on data matrices, but you might not get the results you expect. When I use a minimum on the temperature data, it's going to return the lowest value across the whole data set. Same if I do max. So the highest temperature among all 6 cities, among all 5 days, is 92 degrees. Let's try standard deviation. Same thing. So this is great, but it doesn't really allow us to compare how different the temperatures are between these cities. What we need to do is be able to break it down by city. So there are 2 simple functions. There's row means with a capital M, which will give you the mean temperature over each row. So in this case, it's each day. A similar function is colmeans, C-O-L, capital M-E-A-N-S. And this will give us the mean temperature of those 5 days for each of the cities. Now, these row means and colmeans are very nice functions, but there isn't a row standard deviation. We actually need to use a special function called the apply function. The apply function takes a couple different arguments. It first takes the data of interest, so the temp data, and then we're going to give it the number 1 or 2. If you enter 1, it's going to apply it over rows. If you enter 2, it's going to apply the function over columns. So let's do columns. And then we enter the function of interest, and that argument is capital FUN. And when I do this, it will return the standard deviation of each column. We could also enter the function without naming the argument fun, because it understands the order that we're entering the arguments. From the standard deviation, we can state that over those 5 days, Hawaii has had the lowest variation in temperature. Similarly, San Francisco has been kind of all over the place compared to these other cities. Okay, so what about correlations? When the temp in one city goes up, does it tend to go up in another city, or maybe go down? Well, let's see what happens when we enter the matrix into the correlation function. See, that's very nice. Before, when we've used the correlation function, we would use 2 vectors and enter them in as 2 separate arguments. However, when we enter a data matrix, it looks at the correlations among the columns. So now we have a correlation matrix, and at each point, it will show you what the correlation is between that row and that column. So Seattle and Fairbanks have a positive correlation of 0.45. Mostly the cities are not correlated very strongly, mostly because they are in separate parts of the country and because it's a fake data set. LA and San Francisco may have correlated temperatures as they exist on the same coast. So what happens if we enter a matrix into the table function? It sort of breaks it down by taking all of the different values among the entire data set instead of building a table for each column or each row. And lastly, I want to introduce the summary function, which is very useful, especially when you first load in some data into R. So the summary function will describe some simple characteristics about your data set. It will break it down by column, and it will tell you the minimum, maximum, mean, median, and some quartile information about each of the columns. Now, if you want to get summary stats separated by the day instead of the city, all you need to do is transpose the data matrix before you summarize it. So it's going to be temp data inside of the transpose function inside of the summary function. In this lesson, I showed you how to begin exploring your data set and explain what might be going on or what relationships might exist among that data. In this lesson, I'm going to be showing you how to generate series of random numbers in R. As a powerful statistical language, R comes with many functions that allow us to create randomly generated numbers. These are very useful for different statistical analysis, and we'll be using some randomly generated data sets during this course as simulations. The first random number function I will introduce is called runIf. It creates a random number from the uniform distribution, and it's quite easy to understand. It basically gives you any random number between two values, and you can think of it as random uniform. The arguments that I entered were 1, 0, and 10. The first argument, 1, is the number of numbers that I want it to return. So I want it to return one value. And I want that value to be anywhere between the numbers 0 and 10. If I switch these around, so it's 10, 0, 1, it's going to return 10 random numbers between the numbers 0 and 1. And if we use tab completion, you can see what those different arguments are. So n is the first argument, and then the minimum and maximum. Now we can create a vector from these random numbers. So let's assign 100 random values to x. So runIf 100 between 0 and 1. Now we have 100 random variables. We can also create a matrix if we wrap this inside of the matrix function. So let's say number of column equals 10. Now we have a 10 by 10 matrix, which doesn't quite fit in my console here, but you can see that it sort of slices it up so that it can fit. Now, as a caveat of runIf, I want to introduce the function set.seed. It looks like this. Now, setSeed is a function to allow the user to reproduce a random data set and simulations using any integer. For example, let me create a couple random numbers between 0 and 1, and let me do it again. You can see that the numbers change every time. But if I set seed to be some integer, let's just set it to be 2, and I do runIf with the same arguments, it's going to return 0.18 and 0.7. Now, if I do it again, you'll see that it's sort of random and it's changing. But if I set seed to be 2 again and do runIf, it's going to return the same values as before. So this can be very helpful. Another function that works similarly to runIf is the sample function. We give it a data set to sample from, and it outputs random values from the data set. So for example, let's sample the integers 1 through 10 5 different times. What if we enter in x, the matrix we created before? Well, it's going to go through the 10 by 10 matrix of random values and randomly select 5 of them. So let's say I want to sample the values 0 and 1 100 different times. We came across an error, and it says, cannot take a sample larger than the population when replace equals false. So this is another very important argument to remember when you're using the sample function. The replace argument basically tells the function whether you're allowing it to redraw the same value multiple times. Because I only have 2 values, I cannot set the number of draws to be greater than 2. If I set replace equals true, then we can get zeros and ones and as many of them as it draws for us. So again, think about it if you set replace to equal false. If you set replace to equal false, and you set your data or the population which you're sampling from is the number 0 and the number 1, the first draw, you might take 0, and then when you go for the second draw, there's only one object left, and it's the number 1. So you take that out. And then if you try for a third draw, there's nothing there, and the function fails. If we use the sum function around this sample, we'll see that the number of heads that we get is 48, assuming that 1 is going to be heads and 0 is going to be tails. And every time you do this, it should be pretty close to 50. State.name is a built-in data set that lists the name of the current US states. So if I enter state.name, it returns a vector of all of the names. We can also use the sample function on this. The data set does not have to be numeric. It can be Boolean or string. And if we ask for 10 different polls of the state.name data set, it'll return something like this. The sample function gives equal probability to all items in the data set. We can assign different probabilities to use, however. For example, let's use the sample function again to pull from the integers 1 through 5 1,000 times. We're going to set replace to equal true. And lastly, we can set the argument prob, which stands for probability, to equal 0.2, 0.2, 0.2, 0.2, and 0.2. The vector that we enter as the probability argument needs to equal the length of the data that we're interested in. So when we do this, we've now created this long vector of numbers. We can use the table function on this to see how it breaks down between each number. And you can see that it's pretty close to being 20% for each one, give or take. Now let's create that same vector of integers from 1 through 5, but let's change the probabilities. And again, the probabilities have to add up to equal 1, otherwise it won't work. Now when I do table on S, we're going to see a heightened number of poles from 3 and 4 because we increased those probabilities and we lowered the probabilities of 1 and 5 to 0.1. This has all been pretty uniform so far. I was able to change the probability in the sample function, but what if we want to create a series of random numbers from a different distribution? Now the normal distribution is very popular in statistics. We can create a series of random normal numbers using the rnorm function. So again, think of this as random normal. If we enter one argument, that argument's going to be the number of values that it returns to us, with a default mean of 0 and standard deviation of 1. Now we can specify otherwise. Let's say we want our mean to be 0 and standard deviation to equal 100. Let's create another vector out of these random normal numbers. And let's say we want 100 numbers from a distribution that has a mean of 0 and a standard deviation of 100. Now we can use the mean and standard deviation functions on this vector to see how close they get to the arguments that we specified. So mean of x right now is 18, and the standard deviation of x is 87. So they're pretty close, but not quite. If we increase the number of random normal numbers to 1,000, we should see it converge closer to those values that we entered as arguments. So here it looks much better. Our mean is 5 and our standard deviation is 100. I'm going to do it one more time. It's a pretty nice result. Now, there are many other distributions that we can pull random numbers from, and there are many lists around the website that will show you the different ones that are included in R. In this lesson, I gave you an introduction to generating random numbers, how to set seeds so that you can reproduce sets of random numbers, and also how to take samples from data sets. In this lesson, we're going to have a more in-depth discussion about strings and how to manage and manipulate them. We have already been introduced to what a string or a character vector is comprised of. Anytime we assign variables using quotations, either single or double, we are creating a string. So ahead of time, I wrote a few lines of code, and I'm going to be assigning some different variables, some strings. So the first one is hello for greeting, and then greetings is a vector of strings, and each one has a different greeting. The name world, and a question, what is a pirate's favorite programming language, which of course is R, which is going to be the answer. So we're going to do some work with these. We can use the substring function to extract certain portions of a string. The function works by taking the input string and numbers to define where to start and end. So let's use the substring function on our question. So the first argument of the function is going to be the string that I'm interested in, Q, and then the starting index, which is going to be 1, and the ending index, which is going to be 5. So when I do this, it returns the first 5 characters in that string. That includes W, H, A, T, and then the space between what and is. If I enter 11 and 18 as my starting and ending index, then I get pirates. Now, another helpful function is the number of characters function, NCHAR. And this will simply return a numeric telling you how many characters there are in that string. So we have 49 different characters in our question. Now, we can use this to capture the ending characters of a string, so it actually is very useful. So I'm going to use the substring function. I'm going to capture the last 8 characters of the string. And this returns the word language with the question mark. Now, what this is doing is it's taking the number of characters of that string, which we know is 49. For the index values, the starting index, it's 49 minus 8, which gives us 41, and then the ending index, which is 49. Let's see what happens when we throw in a vector of character strings instead of just a single character string. So we're going to subset our greetings vector, and we're going to go grab the last two characters of each element in that vector. And it will actually return for each element in that vector that operation. So it's returning the last two characters of each element in that vector. The next function I want to talk about is paste, and this function concatenates multiple strings into one. So if I paste my single greeting, which is hello, and the name world, it's going to return hello world. Now there's another argument you add into this function, which is called sep, and it tells the function how to separate the different strings. So by default, it throws in a space, and it looks like this. But if we want no space, all we have to do is put two quotation marks with nothing in between them, and then it will throw them together, kind of crush them together. And you can add anything into the separation argument. But if we want to be grammatically correct, why don't we throw in a comma and a space, and then we'll get hello, comma, world. Now for the paste function, you can throw strings directly into it. So I'm going to add another comma here before the separation argument. I'm going to use quotation marks and put an exclamation point. So that doesn't look quite right. How can we change it? Let's make the separation be nothing. And then we'll throw in another character string here, which will be a comma and a space. And then when we enter that in, we'll get the appropriate looking, grammatically correct hello world. Now you can also put vectors into paste, and it will create a vector of concatenates. If I do paste, we'll throw in the greetings vector. And we'll do it similar to the last paste function we did, with no separation between the different arguments. This is what the function returns. Now we can also pass in numbers, which will be converted into strings. For example, if I want to paste the letter X with the numbers 1 through 10, and we'll set our separation to be just nothing, then it will force the numbers 1 through 10 to be strings and paste them together. Another helpful function is grep, and this function searches through strings to find the input and returns the index number. So for example, I want to search for this character string, capital H, lowercase e, in my greetings vector. So this is going to search in each element of the string vector to find the HE string. When I enter this function, it returns the index values that contain that pattern. grep HE in greetings is telling me that the HE character string exists in the first and third element of the greetings vector. And if we look at the greetings vector, we can see that it's returning hello and hey, so it works just fine. Now we can use this to subset the greetings vector to return only those two values. So if I use a square bracket subsetting outside of greetings and throw in the grep function, it's going to return the first and third values. But there's even a shortcut to do this, which is a little easier. In the grep function, there is an argument called value. And if you set this to be true, it's going to return those instances. By default, value is set to false. But if you set it to true, it's a little easier. Let me show you another example of that. So let's say I want to find all the state names with the word new in it. Remember that state.name is an internal vector that contains all of the current state names. I'm going to set value equal t, and remember, t and true are interchangeable. They're both booleans. And then it gives me all the states that have the word new in it. Or if we want all the capital I's, we do this. Now another function is string split, and this function will split strings based on a certain character value. So it goes str split, and if I throw in q, my long question, and let's say I want to separate it by the space, so I capture each word as a vector. And it works very well. So it split the string q by the string, which is just a space. And there was one between every word, so it worked very well. Now let's talk about sub and gsub very briefly. These functions find matching patterns and replace them with a new string. Let's use the first one, which is called sub. Now I'm going to search for the string pirates inside of my string of interest, and I'm going to replace it with the word statisticians. So the way these arguments work again is we enter the character string pattern that we're interested in replacing, followed by the pattern we want to replace it with, and then lastly, the string that we're interested in doing this operation on. It returned my original question with my substitution. Now, the difference between sub and gsub is that sub will only replace the first occurrence, while gsub will replace all matching cases. So let's look at that real quick. Let's say I want to replace all the spaces in my question with dashes. If I use sub, it's only going to do it to the first space. But gsub, which you can think of general sub, will do it to all occurrences of that string. In this lesson, I gave you a more in-depth look at strings and how to manage them using many different functions. In this lesson, I'm going to introduce times and dates, and these will be important for certain data types called time series, where the index of each observation is tagged with a time or a date. So the first functions I want to introduce are systemDate and systemTime, and these return date and time objects that look like character strings. So the first one, sys.date, has a capital D and a capital S, and it returns what the current date is. And it does it in the order of year, month, and day. So currently it's March 19th, 2014. Sys.time returns the current system time with a lowercase t. You can see that it also returns the date, the current time, and the time zone. I'm going to create a variable, time1 we'll call it, and I'm going to assign it the current system time. We're going to use this a little bit later on. Now we can add and subtract to these date and time objects. So if I enter systemDate and add 1, it's going to tell me what tomorrow's date is. If I subtract 1, it's going to give me yesterday's date. When you add or subtract to systemTime, it's doing it in terms of seconds. So if I subtract 1 from systemTime, it's going to subtract 1 second. And if I add 1, it's going to add 1 second. So if we want to subtract an hour, we have to enter the number 3600 because there are 3600 seconds in an hour. So 4:06 was an hour ago. Now these output what look like character strings, but they're actually a special type of string. So if I use the class function on systemDate, it's going to return date. It's a date object. While time is called a POSIX-CT object. We can take these time types to basic characters or even numerics. The numeric changes the date and time into number of seconds since 1970. This is strange, but it can be very useful. So, for example, if I use the as.numeric function on my systemTime function, it's going to return a very long integer. If I use as.character, it's going to look very similar to the normal output, but it's no longer a POSIX-CT object. It is now a character object. I'm going to create a series of recent dates. I'm going to take my systemDate function, and I'm going to subtract the numbers 1 through 10. So we'll get the last 10 days. Now, this looks kind of funny because the first object in our date vector is yesterday, while the last object is even further back. Maybe a better way to think about this would be to flip it around. So instead of subtracting 1 through 10, I'm going to subtract 10 through 1. And this is going to reverse the vector. So now my dates go in a chronological order. It goes from March 9th to March 10th, all the way to yesterday, which was March 18th. Now, one helpful function is the weekdays function. Let's get a little more information about it before we use it. So this is going to tell us what weekday each date is. It's going to return Sunday, Monday, Tuesday, Wednesday, all the way up through yesterday, which was a Tuesday. The function months will do the same thing. So these are all in March. If I change my date vector to be the last 100 days, and then I do months on my dates, it's going to return December, January, February, and March, all repeated multiple times. Now the sequence function, which we have seen before, which produces a sequence of numbers, can also produce a sequence of dates. Let me show you an example of that. So I'm going to turn some character strings into dates using the as.date function. So I'm going to construct it sort of bare bones first so you can see what's going on. So we're going to go from one character date, which I'm going to put in as.date, to another one, and we're going to go by the hour. So let's say I want to go from July 1st, 2013, from midnight to 11 p.m. on the same day. So hopefully you can see the difference there, but I'm going to be going from the beginning of July 1st to the end of July 1st. And we're going to increment each step by an hour. And for the by function, when you're working with times, you need to use quotations so it knows to use hour increments. So we got an error. And why doesn't this work? Well, as.date changes these character strings that I've entered into just date objects. It strips off the time completely. So it's trying to create a vector of July 1st to July 1st by the hour. So it doesn't really make sense. We need to use a different as.dot function so that it knows what to do. Remember when we used the class function on system time, it told us that it was a POSIX CT object. So all we have to do is replace the dates with POSIX CT. And it works just fine. You can see it returns a series of times, a series of POSIX CT objects, and it increments by the hour. Now for minute, use MIN. And it's going to be much longer, of course. And if I do seconds, it's going to be very large. So let's look at that too. So sometimes when the output tries to print something that's too big, you'll get this error message. It omits a certain amount of entries based on what my max print options are. And that's fine. Don't worry about that. It's still there and it was still calculated. It just can't show it all in the console. Now we can do something similar with more recent timestamps. If we subtract the vector of integers from 12 going backwards to 1 times 3600. And this will give me the last 12 hourly timestamps. Now I'm going to create another variable called time2, which is going to be the current system time. You can remember that earlier on, we created this variable time1. Now we can figure out how much time has passed since I started this lesson by subtracting these two times. I'm going to subtract the further back time from the more recent one, and it's going to give me how many minutes have passed, 8.67 minutes. So this operation on these two time objects will give you the time difference. Another way of doing this is using the diff time function. So if I enter time 1 and time 2 as the two different times I want to calculate the difference between, it will return negative 8.6 minutes. And that's because it's subtracting time 2 from time 1. So we can switch them around. And we can also specify another argument called units. Let's say we want to know the number of seconds instead of number of minutes. Or we can even do hours, days, which of course is very small because it's a very small portion of the day. And if we put this inside of an as.numeric function, it won't return this character time difference of number days. It will give us just the number. And that can be very, very useful, especially when working with time series data. Working with times and dates can be confusing at first, but this is meant to be an introduction to get you thinking about how these work. Once we start generating time series objects and manipulating them, this information will become much more useful, and the relationships between the functions will become more apparent. At this point, you should be able to create dates and times and sequences of dates and times. Later, we will learn how to work with irregularly spaced sequences of time.